We have some topological coupling of the axion to the photons, and we have the coupling of photons to some electromagnetic current. And I am normalizing my fields in some particular way. So let me tell you how I'm normalizing my fields. Theta is a scalar of period 2 pi. It's not canonically normalized. You have to multiply it by this constant f, the axion decay constant, to canonically normalize it. My photon field is not canonically normalized. It's a U1 gauge field with coupling E. What that means is that if I do a U1 gauge transformation e to the I alpha, then my photon field shifts by the derivative of alpha. That's how I'm normalizing my photon. Related to that statement, integrals of J over closed three-dimensional manifolds are integers. So we have quantized U1 charges. And to compare what I'm going to tell you to how you usually see the coupling normalized in the phenomenological literature, if you look at papers on axion photon couplings, they generally talk about some parameter called GA gamma gamma that people conventionally normalize with a 1/4 in front, a canonically normalized axion field A, and a canonically normalized photon field. Let me put a hat over it so it's canonically normalized. Okay, so when you look at experimental plots where people search for axions, this is the thing they're mostly searching for. Things like ADMX or DM radio, haystack, all these different kinds of axion experiments are looking for this guy. Okay, so the question is, what do we expect this coupling to be? And to relate it to what I wrote above, we take into account the normalization. People often call f over n the axion decay constant because that's what appears in the gluon coupling. So if I factor out that f over n, what I have left from this coupling is an e over n. Put in the extra factors to canonically normalize things. And then there's another piece, which is about 1.92. This piece comes from mixing with the pi 0. It is not quantized in any particular way. It's just some number. It depends on the up and down port masses. I would say secretly, this is really a coupling. This is really a derivative coupling. Or it's a coupling that's proportional to the axion mass squared. The axion mass is small, so you would think this should be small, and most such couplings are small, but because the axion mass and the pion mass have the same origin in QCD dynamics, it turns out this thing is like ma squared fa squared over m pi squared f pi squared or something roughly like that, and so it's an order 1 number.
So this is only really for the QCD axion.
This is for the QCD axion. Yeah, I should say a lot of what I'm going to talk about, I will say things specific to the QCD axion, but I will also say some things that are just generic statements about axions coupled to U1 gauge fields. Right, but this piece is specifically for the QCD axion. Thank you. Whereas this piece, this e over n, in simple models, this will be a rational number. Why is it a rational number? Well, I'm going to give you a better reason, but what you'll find if you just do the calculation in simple models, this n and this e are some anomaly coefficients. They depend on charges that things have in the theory. These charges, you have charges showing up here. You have Dinkin indices of some representation showing up here. Everything's a rational number, and so you get a rational number. Okay, so my main claim that I want to convince you of, and there's going to be some other interesting physics related to this, is that n and e are integers. They have to be integers for fundamental consistency reasons. Well, Or maybe 9e is an integer, because charge comes in units of a third. Which one of these is the right answer? It depends on the global structure of the standard model gauge group. If it's SU3 times SU2 times U1, or SU3 times SU2 times U1 mod Z6, you'll get different answers. Okay. The statement that n is an integer, I think, is completely uncontroversial. I'm not aware of anybody trying to argue otherwise. This claim is somehow apparently controversial. I didn't think it was controversial until a year or two ago when I saw people writing papers claiming otherwise. Then I realized there are even older papers that claim otherwise. In fact, if you look at the Wikipedia page about Axions, it has the wrong equations of motion and claims that are inconsistent with this. So I want to try to get the story straight. Okay, let's start with n, the coupling to gluons. Here is a fact about SUN gauge theory. One over 8 pi squared times the integral of this g wedge g term, g tilde, over any closed four-dimensional manifold is an integer. This is just a fact about SUN gauge bundles. This is the integer that we're used to as instanton number. Okay. When I tell you that theta is a periodic scalar, what I mean is that theta and theta plus 2 pi are literally the same thing, meaning this is a gauge redundancy. The theory, theta is not a gauge invariant field because it's a periodic field, and so the value of that field doesn't have a meaning. It's only well-defined mod 2 pi. So e to the I theta has meaning. Derivatives of theta have meaning. Theta. Okay. So the well-known argument that the coupling to gluons of an axion is an integer is that our action, this integral theta trace q and g, is not well defined. It's not gauge invariant. But actions don't have to be gauge invariant. Things that show up in path integrals are e to the I action, or if I'm in Euclidean signature, e to the minus action. E to the I action has to be well defined. If I take this term and I shift theta by 2 pi, I pick up a new factor in e to the I action, which is e to the 2 pi I n times this integral. This integral is an integer. If I look at the smallest integer it can be 1. This thing had better be trivial to make my path integral well defined, and that only works if n is an integer.
This is for topology S4.
This is for any closed spin or manifold. Yeah. So that's the mathematical fact that's underlying this. So we can define this quantum field theory on any four manifold we want, and for it to be well defined, we need this n to be an integer. Okay. Any other questions about that argument before I move on? This is kind of the...
So M4 doesn't have to have trivial by 1, or is there any condition? So
it doesn't have a boundary, but other than that, it's any.
Works for a torus, for T4. Yes.
Okay. So axion couplings to gluons have to have some quantized integer in front. or the path integral just doesn't make sense. We don't have a well-defined form. Okay, so if there were no questions about that, let me give you another fact. Okay, and then I'm going to give you what looks like a completely analogous argument, but it's going to turn out it's a little bit more subtle, and the subtleties are going to be where everything interesting about the talk, I think, happens. But here's another mathematical fact. If I have a U1 gauge theory, and I put it on any four-dimensional space-time closed spin, and I integrate f wedge f. I get an integer. I get an integer times 8 pi. So there are no instantons. Actually, there kind of are instantons, which is the thing I'm going to get to. But naively, there are no instantons for U1 gauge theory on S4. There's no solution you can find that looks like the instantons for SUN. But we could do other things. We could put the theory on a torus, a four-dimensional torus. I can turn on magnetic fluxes through two-dimensional tori. So I can factor it into two manifolds. I can put flux on each of them. I've normalized my field in this way that I told you over here. That way of normalizing fields guarantees that magnetic fluxes, integrals of f over any closed two-dimensional surface are 2 pi times integers. And so, given that each of these have integrals that's 2 pi times an integer, you might think that this integral should be 4 pi squared times an integer. And in fact, that's the right answer if you allow completely general things that are not necessarily spin with spin if the answer is squared. So, okay, so just repeat the argument.
Sorry.
Does it assume that it's compact U1?
U1 is compact, that's what I mean by U1.
Well, but it assumes that it's U1 and not R, right?
Yeah.
Because in principle,
yeah,
that's already a choice
yes.
to make, right? So
right. If the gauge group is R, charge is not quantized.
Right.
Neither are these. Neither is this the coefficient of this.
So there was this assumption.
In that case, this integral is just 0 on any man.
It's just my ignorance, but maybe other people are too. When you say spin,
yeah,
what does that mean?
I mean a manifold that I'm allowed to define fermions on, basically.
Oh.
So things that have a spin structure. So anything we care about for the real world should be spin.
I didn't know.
At least more or less. Yeah, so like CP2 is an example of a four-dimensional manifold that is not spin. But for my purposes, I'm interested in real-world particle physics, so I don't care. Anyway, even if you drop that, it would just be a factor of 2 difference in the things I'm going to say. It's not very important. Okay, so we can repeat this argument, and what we learn is that this coefficient E is an integer. Here I've normalized things to the smallest U1 charge is 1. In the standard model, the smallest electromagnetic charge that we have is 1/3. That's why the right answer might actually be 9e as an integer. But there's also this subtle thing where the Z3 subgroup of hypercharge acts on the standard model fields in the same way as the Z3 subgroup of SU3. And so there's this question of what's the right global structure of the gauge group. And if you pick SU3 times SU2 times U1 mod Z6, which is what happens if you start with a gut and break, for example, then it's just this, even in our usual normalization where charge is 1/3. Okay, so that's another subtlety. That's just some integer number that modifies some of what I say, but it doesn't qualitatively change anything. Okay, so this is a simple argument. I think it's relatively well known, and yet recently people have been questioning it, and so I want to explain why you might question this. Okay, so This coupling E was for everything normalized in this way that I did over here, but as I said, the coupling you actually measure, GA gamma gamma, you canonically normalize your fields. And when you do that, your coupling has this factor of alpha in it. And so my canonically normalized gauge field has an extra factor of E. And so I see a factor of alpha, and that wouldn't surprise you if you think about some UV completion where this coupling is really coming from a loop like that. I have factors of E in both of these couplings. Now, at this point, you might reasonably ask, what's so special about the coupling E? Right? E is the electric coupling of electromagnetism, but there's also a magnetic coupling. Right? You can dualize electric fields to magnetic fields. Magnetic fields couple with strength 2 pi divided by E. So what about this argument picked out E as opposed to 2 pi divided by E?
I mean, you're defining the theory to have weakly coupled electrically charged particles as opposed to weakly coupled magnetically charged particles. So I feel like it's part of the definition.
Yeah,
right?
That's basically right.
Okay.
I'm going to spend the next, I don't know, 20 minutes giving a more long-winded version of the argument you just said, basically. But, right. So let me say a couple more things about this electromagnetic duality thing, because if you just start with this action that I wrote down over here and derive the equations of motion and write them in the way we usually write Maxwell's equations, you get the equations of Axion electrodynamics. And they look like the ordinary Maxwell's equations with some extra terms. And so one thing that you get is the divergence of E now has a piece that depends on this coupling of the axion, GA gamma gamma, and a magnetic field added into the gradient of the axion field. Another thing that happens is the curl of B has a new term. GA gamma gamma times magnetic field times the time derivative of the axion plus electric field across the gradient of the axion. And it turns out the equations for divergence of E and curl of E are unchanged. Okay, so these are the equations that you get in the usual way. Just start with this action, vary the field, see what happens. And these things show you that the axion coupling that I started with over here explicitly broke electromagnetic duality. I got a new term on the right-hand side of divergence of E that looks like B gotten into divergence of A. I got no such new term in the divergence of E. Okay. This is just a fact about axion electrodynamics. If you look at the Wikipedia page for axions, you see a different set of equations than this, where every time I have a term like that, they put a corresponding term here. Because some people wrote papers where they made up these equations, and these equations are wrong. But there's this new set of papers that are trying to convince experimentalists that they should be looking for those effects that depend on other terms in these equations. Okay. So that's why if it seems to you like I'm just being pedantic about deriving basic things, that's why I'm doing it. I think we need to sort this out so that people don't go building experiments that are looking for effects that don't actually exist in quantum field theory. Okay, so we see that these equations broke this electric-magnetic duality symmetry. Another thing that breaks electric-magnetic duality is the Witten effect. Okay, and that's kind of the heart of my story. So let me remind you about the Witten effect. Here I don't have to talk about an axion, I can just talk about a constant theta angle. So I just have a theta term in my Lagrangian. If I have a magnetic monopole, some magnetic charge, okay, normalized to be an integer multiple of the base unit of magnetic charge. this acquires electric charge, UE, which is magnetic charge times theta over 2 pi. This is something that Witten derived. His paper was originally written in the context of the Polyakov monopole, but in fact, this is a general fact about this effective field theory. No other assumptions needed. And one way to derive the Witten effect is the following. You say, think about a magnetic monopole in some region where theta equals 0. If I zoom in near the monopole and measure the magnetic flux around it, I'll see a non-trivial magnetic flux. If I measure the electric flux, I won't see anything. It's purely magnetically charged. But now let me turn on a non-zero theta, just as a background field. Okay, I'm just defining my Lagrangian to have this theta f wedge f term where theta is some explicit function of space that I'm just putting in by hand. Okay, and so you imagine theta has some profile, which is sort of 0 out here and then turning on out here. Now let me build a surface out here and measure electric flux. And I'll get a non-zero answer. I'll get a non-zero answer because this equation up here tells me I have a gradient of theta that I've turned on here, a radial gradient of theta. And I have a B field coming from my monopole that's also radially outward. And so I have a B dot gradient of A. And so that becomes a source that gives me a divergence of E, and that gives me an electric field. Okay. So if I'm an observer out here, and I don't look at what's happening near the monopole, I just say, oh, there's some object sitting there, and it's electrically charged. Okay. And then we can sort of take the limit where we bring this surface in and make it arbitrarily small, and it looks like this electric charge is just living on the monopole itself. So this is one derivation of the Witten effect. This derivation, as far as I know, was first written down by Wilczek.
But it took some energy to have your non-uniform theta.
Yeah, here I'm just putting it in as a background.
I know, but why would that be a good assumption about nature?
This is not, what I'm doing here is not really an argument about nature. It's just an argument about kind of this effective theory in the presence of a background. So I'm just turning it on as sort of a theoretical construct. But the claim is that if we have an actual axion, the same kind of thing will happen. And there, as you say, I wouldn't be able to easily set up this gradient because how do I source an axion
It seems
field
like
like
you'd
that?
have to talk about what minimizes the energy and whatnot.
Can I make a comment?
Yeah.
Yeah, so there's a paper by Fischler and Prescott
Yeah.
who did exactly that of minimizing the energy in the axion case, and they look at the gradients you get, and they're doing precisely what you're asking.
And it does minimize the energy to have the axion there.
Yeah, there's a variation you get in the axion, and there's a variation in where the electric, there's an extended electric charge density in that situation. It's a very nice paper.
Thanks. Yeah, in fact, that paper is closely related to another thing I'm going to get to in a little bit. So, there are several different arguments for this. Some of them are even more abstract than this. Basically, the thing that has quantized electric flux turns out to be basically just the what am I saying? The thing that has a quantized integral over the surface turns out to be basically just the canonical conjugate of the gauge field, which is like 1 over E squared star F minus theta over 4 pi squared F, something like that, which just comes from varying this thing with respect to the field strength. So this thing has to be an integer. And what's happening here is the magnetic flux is an integer. So this part is not an integer, and so this part also has to kind of shift to also be not an integer to make this combination an integer. There's a bunch of different arguments, but I think this Witten effect is well established. It's not special to the Polyakov monopole. It's just a property of this kind of effective theory. And it's related to this fact that the fact that what's happening here is magnetic monopoles are getting electric charge in a theta background, but electrons are not getting a magnetic charge in a theta background. That's coming from some explicit breaking of electric magnetic duality, which is also reflected in these equations having this term and not having the E dot gradient of A term. Okay. Another related thing. I've been talking about electric magnetic duality. Let me remind you some things about what electric magnetic duality does. I have electric and magnetic currents, and electric magnetic duality for free Maxwell theory, just a free photon, is some group of 2 by 2 matrices that acts on these currents like this. And this group, this is an element of SL2Z. So these entries are integers, and the determinant is 1. Other things transform under this. One thing that transforms under this is I can package the theta angle and the gauge coupling in this complex combination and call it tau. And when I do this kind of transformation on my current, tau maps to A tau plus B over C tau plus E. In particular, one element of this matrix 1, 1, 0, 1, we call T, replaces theta with theta plus 2 pi. It adds something to the real part of tau. It's just tau goes to tau plus 1. So that's one way in which some of these statements I've been making about the periodicity of theta are somehow related to this electric magnetic duality group. But another thing also happens when I do this. So if the currents are changing, and I want to maintain some structure where I can think I have some electric gauge field that couples to the electrically charged things, and I have some magnetic gauge field that couples to the magnetically charged things, then my electric and magnetic gauge fields themselves have to get rearranged by this duality. And they do, and one way that I can package that is if I organize them like this. I put a magnetic version of my field strength. This is like derivative of some dual magnetic photon field here, and I put my ordinary field strength there. This thing gets mapped again to A, B, C, D, magnetic minus electric. And if I act with this matrix, the one that shifts theta by 2 pi, in particular, I find that this T operation, I get 1, 1, 0, 1 acting on this. It doesn't touch my usual photon. F goes to F. But it does touch my magnetic photon. Magnetic photon goes to magnetic minus electric. Okay. So,
And FM here is not tilde F.
FM is, right. FM is the thing that we want to be the magnetic field strength, which you should define by looking at this thing that has quantized flux.
Yeah.
And equating it with 1 over 2 pi FM. Okay, and from that description, you can also see why this happened. If I shift theta to theta plus 2 pi, I add a term proportional to F here, and that's this term that got added there. But the reason you have to do this is that this is the thing that behaves like a magnetic flux. This is the thing that has an integer value when you integrate it through some surface. And so if you want to construct a dual U1 gauge field, it has to have that property. So the only way that you'll get sort of charge quantization right for your magnetic degree of freedom is if it knows about this theta transients. Okay, so we have this set of correlated facts.
So that's
Yeah.
So this is not what the magnetic charge, because to define the magnetic charge, you take a two-dimensional surface away from your charge at infinity, you integrate F, not star F.
Right. If you want to measure a magnetic flux, you integrate F. But now I'm trying to dualize, so I would have a dual magnetic photon. The magnetic flux of the magnetic photon is like the electric flux of the original theory. And the thing that is the right sort of quantized version of the electric flux is this one. So, okay. So I've told you some set of facts here, and they're all related to each other. Axion equations of motion have this special term in them that B is dotted into the gradient of A. They don't have a term with E dotted into the gradient of A appearing and sourcing a B field. Relatedly, electric magnetic duality leaves our ordinary electric gauge field alone when I shift theta by 2 pi. It does not leave the magnetic gauge field alone, it changes it. Okay. So,
but isn't there some other A, B, C, D that would do the
Yes.
opposite?
yes,
It's a group.
you're getting ahead of me, but yeah, I'm getting there. Right, so let me first just point out where was my secret assumption? Okay, so somewhere in here I built in an argument that picked out the electric coupling. I told you that the Axion coupling GA gamma gamma that we were deriving had this factor of alpha in it that involved the electric coupling E, not the magnetic coupling. Where was I hiding my assumption when I derived it? Does anybody see where I hid the assumption?
Local operator with F minus
Yeah.
A wedge J, right? Already A wedge J breaks this symmetry.
I started. Well, I could have imagined there were magnetically charged things here too. But yeah, so I did everything in terms of F. Okay, I defined my path integral in terms of some U1 gauge bundles that are bundles of A, and I coupled my axion to that F. And when I gave you this argument, okay, let me just down so I can find it again. In the SUN case, I did something totally innocuous, which was I said, okay, I couple my axion to gluons, I shift theta by 2 pi. When I shift theta by 2 pi, I pick up this new term, e to the 2 pi in times this integral. I did the same thing with the electric thing here when hidden in this word repeat. Okay, I coupled my axion to F wedge F. I said I shift theta by theta to theta plus 2 pi. I pick up a new term, e to the 2 pi I e integral 1 over 8 pi squared F wedge F. When I did that, I assumed that when I shift theta by 2 pi, nothing happened to F. I did not get other stuff on the right-hand side of this where I pick up pieces that came from new things happening to F. And that is what we see here, is this assumption. We've isolated this electric thing that didn't change, but there was also this magnetic thing that did change. Right. So one way to say Martin's question is, what if we coupled the axion not to F, but to this thing? Okay, and then that thing shifts, that thing changes when we shift theta, and so things are going to look a bit different. Okay. Okay. So. Okay, so I'm going to come back to that question of these alternative couplings. But let me first say some more about just the usual coupling. Okay, so with the standard story we have here, we have the Witten effect. I told you about the Witten effect when theta was just sort of a fixed number or background field, but we have an axion, theta is dynamical. When theta is dynamical, this means the monopoles charge vary continuously. And whenever that's true, we have some new piece of physics, which is there has to be some way to change the charge of a monopole. And this is what's known as a Dion collective coordinate, or zero mode. This was first derived by Jakiv in 1975 or 76 or something like that in the context of the topology monopole, where you can just explicitly check. You have your classical solution for the monopole, you ask what are the zero modes? There's 3 obvious zero modes that pick up the monopole and just move it around in space. But there's another zero mode that comes from sort of some gauge transformation that isn't vanishing at infinity, that sort of excites this extra mode that gives the monopole electric charge. And I think one reason why people are getting confused about this subject is that all of these sort of foundational papers are phrased in terms of the topological monopole. But actually, all of this physics just depends on the original effective theory that I started with, not on any details of the UV condition. So how does this work? There's this degree of freedom, sigma, that lives on the world line of the monopole. Okay, it's localized along the monopole world line. So I'm writing it as a function of some kind of proper time that you measure along the world line. And it's a periodic scalar. It's a quantum mechanical degree of freedom. It's like a particle on a circle. And so the eigenstates of the particle on a circle are just things with some integer number of units of momentum around the circle. And what those integer units of momentum correspond to is giving the magnetic monopole integer amounts of electric charge. But we should also be able to give it fractional amounts of electric charge, and we do that by coupling this degree of freedom to the axion. So what we have is a world line EFT. Okay, I integrate over the monopole world volume, things that depend on this mode are some kind of kinetic term for this mode and a coupling to theta. And I'm writing this in terms of this thing I call dA sigma. That's just a covariant derivative, because sigma, it turns out, isn't just a 2π periodic scalar. It also shifts when you do a gauge transformation of your original gauge field A. So when A goes to A plus B alpha, sigma goes to sigma minus alpha. Okay. This is the right effective theory. One way you can check that is, okay, there's another coupling that I didn't write here, which is the coupling to the magnetic gauge field. Right, the monopole is charged with the magnetic gauge field, so I should have a coupling that integrates the magnetic gauge field along the monopole world line. When I do this operation, my magnetic gauge field is not gauge invariant when I shift theta by 2π. It picks up a new piece, which is a multiple of A. So this term alone would not be well behaved when I shift theta by 2π. But now I pick up another term, which is theta times the A that's living in this covariant derivative. And I think I might have mixed up a sign convention somewhere. Maybe I want a plus with these conventions. But it'll cancel. Here I get an extra minus A, here I get an extra plus A. And the whole thing is well defined. Okay, so this is in fact the form of anomaly inflow, although nobody used the words anomaly inflow at the time that this was originally discovered. It was like 10 years later that people understood how to talk about this. Okay, so we have this theory. We have a quantum mechanical particle in a circle. I can look at the energy of the modes as a function of theta. And I have some quadratic function. I have an energy of my nth mode. It's proportional to n minus theta over 2π squared. So I have an n equals 0 mode that's just a parabola. And then I have all the other modes, and they're also just parabolas, but with minima at different places. Okay, so maybe you've done this exercise just with a quantum mechanics class, solve particle in a circle, with this topological term in the action. This is what you get. So the energy of every individual mode is not a periodic function of theta, but the collection of all the modes is, because each mode is sort of shuffling along to become the next mode when you shift over by 2π. Okay, so this is an example of what in general is called monodromy. You have a spectrum that's invariant under this circling around in theta, but every individual mode is ending up at a different place. Okay. The time again. Okay. Are there questions about what I'm telling you so far? Okay. So this physics is, I think so far I haven't told you anything that there wasn't someone who understood probably before I was born. But now let me tell you something that, as far as I know, nobody had pointed out before, which is what was pointed out in this paper I wrote with Gigi Fan, Katie Fraser, and John Stout a couple of years ago. We have these Dion modes, and they have theta-dependent energy. Okay, and this was also pointed out in the paper that John mentioned by Fischler and Preskel. They did something interesting, which is they studied what happens if you have actual physical monopoles, like you have monopoles and anti-monopoles in the universe. There's a theta-dependent energy, so these things shift the effective potential of an Axion's field. Yeah.
Is that theta position dependent? Is it theta of X?
Yeah. This is the Axion field, and so evaluated at some point on the monopole world line.
Then how is the energy spectrum? Like, theta appears in the energy spectrum, right?
Yeah, what I'm writing here is just what the energy would be if theta was just like a fixed constant value.
I see.
But here we're making it dynamical now. We're coupling this to an Axion background. And so the monopoles are going to acquire electric charge as a
The
function
spectrum
of
is
the
more
Axion.
complicated in that case. The spectrum is not.
Yeah, it doesn't really make sense to talk about a
Yeah.
discrete set of modes in this way, because now theta is a continuously varying thing. And your monopole is sort of locally acquiring electric charge and extra energy depending on what the Axion is doing in the neighborhood of the monopole. But of course they're coupled together, and so the whole thing is more complicated. Okay. Now, whenever we have some heavy state whose energy depends on the value of some light field, we can integrate out the heavy state and get some non-trivial effective potential for the light field. And this is the thing that mysteriously, as far as I can tell, nobody did until we did it 2 years ago, even though it could have been done in 1985 or something. All the ingredients were there. So the claim is that virtual monopoles generate an Axion potential. Okay, so what we want to do is integrate out loops of magnetic monopoles and see what kind of potential for the Axion do these give rise to.
So
yeah,
obviously, your monopoles in reality are gonna come from somewhere, and people consider the Polyakov monopole because that's one way in which you can have these objects,
yeah.
in a way that you don't have strong coupling, so you can think about those in those ways.
Mm-hmm.
But I can also compute this effective potential by just looking at whatever non-abelian gauge theory I have that after breaking is gonna give me these monopoles.
Mm-hmm.
And then this Axion potential, I suppose, is just going to be generated by the non-abelian instantons, right?
You're getting ahead of me again. Yeah.
Right.
That's where we're going. Yeah. In that case. But we don't need to assume this came from a non-abelian UV completion. And there are other UV completions for monopole theories. You can just get U1 gauge fields out of string theory, and your monopole is some kind of debrane. It's like a fundamental object. Everything I say here applies. Okay, so we have these monopoles. We want to integrate them out and calculate the effective Axion potential. And how do we do it? Well, we don't have like a monopole field in our Lagrangian that we can vary. It wouldn't make sense. It's a strongly coupled thing. What does make sense is to think about some kind of semi-classical method. Okay, so in the path integral, how do we integrate over monopoles? Well, we sum over their world lines. We make loops of their world line in the Euclidean spacetime, and we have a known action along the world line, which is the thing that I wrote here. And we just work out how does this work? And okay, so you write some sort of standard world line thing. Just like you would for integrating out any heavy particle of some mass, but now I'm summing over all the different Dion modes, all the different ends. Every one of them has a mass with some formula that we know that depends on theta. Their mass is a sum of the basic mass of the monopole plus this extra energy that's theta. Okay, but this sum is awful because as I said, every one of these masses is not a periodic function of theta. We want to calculate some potential, which is supposed to be 2 pi periodic. So what do you do? The one person who knows what you do is Martin, who did exactly this calculation, basically in a different context of extra dimensions where you integrate out Kaluza-Klein modes. So there's a trick that you can Poisson resum a series like this and get a different series. Okay. So I think I originally learned about this trick from this paper by Martin and Xinsha Chung and Konstantin Mach. Poisson resum. And you get some formula, which is a different sum over a different set of integers, not n anymore. I'll call them L. And now every term in your formula has this explicit e to the IL theta. So you're getting the harmonics of the potential. Okay, and then you have, sorry, I didn't write my integral detail. Then you have this thing that depends on your monopole mass and on this number L, this parameter L that showed up in my effective action. Okay, it's some function of tau, and you have both a tau term and a 1 over tau term. And now you can find a saddle point. It's like a balance between these terms.
And so this m sub n is that energy?
This is m sub m, capital M, that's just the monopole
Previous formula,
mass.
the one that you put on.
This is the mass of the nth Dion mode. And so m sub n is like the basic monopole mass m sub m plus this correction that depends on theta. Okay, so you Poisson resum, you get a series of harmonics. Each one has a saddle point you can calculate. And so there's some action of the saddle. Turns out to be the geometric mean of the monopole mass and this length scale L that appeared here.
So your integral looks sort of divergent at small tau. That integral looks divergent for small tau, doesn't it?
Integral looks divergent for small tau. It may actually be divergent at small tau. Yeah, but the saddle point is at big tau, and so we're just sort of trusting that.
So it's not. I shouldn't trust this for small tau, I guess.
If the saddle point came out at small tau, I don't think I would trust it, but that's not where the saddle comes out. And there's potentially higher order stuff in this world line effective theory that changes the behavior away from where the saddle point is. And we sort of checked that if you put in like higher powers here, they don't affect things much near the saddle as long as this action comes out to be big. So we kind of trust it.
Well, what is the parameter that you're taking large to do the saddle point?
Good. So what we're assuming here is basically that this L sigma. So in the example of let's see, how does it work? In the example of the Polyakov monopole, this L sigma is like the monopole mass divided by the W mass squared. And so that's some long length scale. And then it's showing up here in this combination, which is a big number. So basically that's the thing. Which is related to the next thing I wanted to say, which is if you work out what this is for the Polyakov monopole, you get 8 pi squared over g squared, where g is the SU2 gauge function, which is what Isabel was anticipating. So we think that these things in the Polyakov case, these U1 instantons. Okay, so what do I mean by instanton? Sorry, I failed to say something important here, which was that this L has an interpretation as the winding of the Dion mode. Okay, so our monopole world line makes a loop. Sigma is a periodic variable. And you can think of this as sigma is going around L times and coming back to where it started. So L is like a winding number. And so you can think of these monopole loops with this Dionic mode winding around the loop as a kind of abelian analog of a non-abelian instanton. And what we're seeing is in the case where we can compare, they actually have the same action. And we think they're really sort of the same thing. Okay, so you have your small size SU2 instantons around the scale of the Higgsing. You should sort of convert to somehow describing them in the U1 language, and this is kind of what they are.
Matt, you very possibly want to get to this at the end, but let me ask the question now, just in case. I've never understood whether it's really true and how to see this mode, whether there's a Dion mode for a magnetically charged black hole, right? Because I would expect there should be the same shift of the electric charge.
Yeah.
And how I do that, and whether I can start, I mean, I'm going to ask the question about whether you take the monopole mass here, the scale of breaking so large that I should start thinking about this monopole actually being, you know, inside horizon.
So I can tell you an example that I think it sheds light on this, which is that Kaluza-Klein monopoles, if I just take a gravity theory, compactify on a circle, I get a lower dimensional theory with a U1. It has a monopole. That monopole is just some solution to the higher dimensional GR theory. That monopole does not have a Dionic mode. There just is no such mode. There's no way to boost it around the circle and get a different state. There's also no Axion. If there was an Axion, I would think I would have to find a Dionic mode. I don't find a Dionic mode. I don't find an Axion. But there are Dionic black holes. If I go to big enough mass, I can make black hole states that have both magnetic and electric charge. But if you look at what's the right way to say this? You look at the curve in the plane of electric black hole charge and magnetic black hole charge for Kaluza-Klein black holes, and you look at the curve of fixed mass, you get some shape which is concave. For Reissner-Nordstrom, you would get something like that, that's convex. And so what this is telling you is that somehow these things sort of want to repel each other, which I think is like saying that the fundamental monopole had no Dionic mode, so there doesn't want to be a bound state of electric and magnetic charge. You have to kind of put in extra energy to force them to come together. So I
don't understand what the blue means.
I think I said it the right way. I think I'm drawing contours of constant mass of black holes, of extremal black holes, I should say, extremal black hole solutions in the plane of the electric and magnetic charges. And it's because the scalar, the radion is coupling in some particular way. They don't behave like Reissner-Nordstrom black holes, and they have this concavity property. And so what I think I want to say is when you find this concave shape, it means you can make Dionic black holes, but your elementary monopole did not have a Dionic mode. But if it's convex, I think I would expect to find the Dionic mode for the elementary monopole, so we're just scaling down the black hole. But I don't want to linger on this too long because I'm almost at the end of time and I want to get back to the other thing, so we could chat more later. Okay, so the claim is there's a calculable Axion potential that comes from loops of monopoles, and it's a semi-classical thing, and we can estimate it, and everything seems to be well behaved. Now let's go back to the other question of the Axion photon coupling.
Sorry, may I ask about this one?
Yeah.
Let's say just usual QCT action, but we have a SU5 theory, so there is double coupling. So I think there is different additional contribution to QCT potential, QCT action potential, which comes.
Yeah, I mean at small scales there are only SU5 instantons, but once you go below the scale of SU5 breaking, they sort of become different kinds of instantons, and they all contribute.
No, but that contribution to the potential, it should be added to usual QCT contribution.
Yes.
And it's automatically.
But it's like a small instanton, so it's probably not very important, right? The Axion gets most of its mass at the confinement scale, and the small instantons don't matter very much. So I think it's probably not very important.
Well, but we could have theories. I mean, there's lots of SU5 theories where there's tremendous amount of matter content, and
yeah,
alpha at that scale becomes semi-perturbative, right? Or
yeah,
right?
if you play games with the running, you can maybe make it.
So what you're saying is that this assumption that there is a theta FF dual coupling effectively means that that's coming from some theta coupling to some other non-abelian group, potentially SU5 or something else.
It could be, but I mean, like I said,
Or
there are examples
general,
that don't have non-abelian UV completions. So all of this is derived within the effective theory.
Right.
I'm just saying that within certain UV completions, these things might be the same objects as something else that you already knew about.
Yeah, but I guess your point is that the theta effective coupling necessarily implies that, there's something like that as well as the.
Yes. Yes, so I would claim that any axion that couples to the standard monophoton has some new contribution to its mass that comes from monopoles.
And that doesn't need to be like aligned with GCD contribution.
It does
But
not.
it might
It does
suppose
not.
it might suppose strong CP.
It could if it's big enough. I think probably in most models it's not that big.
So it's like any other UV contribution.
Exactly, yeah.
But you're saying there is calculable source of it in.
Yes. Actually calculating it for the standard model is hard because I haven't put in light fermions, and as we know, instantons have Fermi zero modes. And for this case, that's related to the Kalin-Rubikov effect, which is a very confusing literature. I think I kind of have a handle on how to do that calculation now, but I was confused for a while.
Yeah, incidentally, the Fischler-Preskel paper makes a big deal the existence of fermions tremendously changing the structure of the
Yeah,
calculation.
if you take some of the words they say or some of the words Kalin said in this first paper too seriously, you would think the action actually changes a lot. And I think that's not right. I think what changes is the prefactor, just like we're used to for non-abelian instantons, right? You get factors of the masses or Yukawas in front. I think that's the right answer, but we have not worked that out enough for me to feel like I can give a talk that has all the details of that.
But can you say if it spoils the strong CP problem solution, or?
I think probably the minimal thing does not, but in certain UV completions, if the couplings are becoming stronger in the UV or something, okay, sorry, we're actually already past 3.
Oh, but you
Okay,
should
maybe 5
continue.
minutes.
We're
Okay,
spellbound.
if anybody needs to leave, please go ahead.
Just think of yourself being in Minnesota.
It's a very different audience here. Okay. Right. So I wanted to get. I wanted to get back to this thing about could there be a different axion photon coupling, right? So I had the theta F wedge F coupling, and basically what we saw was this implied multiple things that are correlated. One is the Witten effect on monopoles. And the other is GA gamma gamma was proportional to alpha times rational number times whatever calculable factors with the 8 pi or whatever. And so now we can ask, what if we couple this differently? What if I couple the axion in a different duality frame, right? So what if I write theta F prime wedge F prime, where F prime is an SL2Z cousin of F? Can I do it? And the claim is, well, in this case, you might get GA gamma gamma as something more general, maybe even much bigger, depending on 1 over alpha instead of alpha. This is the kind of thing people have been writing papers about in the last couple of years. But now you get a dual Witten effect. Okay, because to do this, it means that your original gauge field F is changing when you send theta to theta plus 2. So now electrically charged things, like electrons, get a magnetic charge in an axion background. That's an unavoidable consequence of trying to get these other kind of couplings. Okay, and if you start to think about electrons getting magnetic charge in an axion background, that sounds really bad phenomenologically. Okay, so let's just say a couple of words about that. When theta goes to theta plus 2 pi, this means the electron becomes a Dion with magnetic charge. If that state had the same mass as the electron, that would be a disaster because we would have already seen it. So it better be heavier, right? So we better have this kind of monodromy picture where as a function of theta, I have the mass of the electron starting out at some non-zero value, getting bigger as theta increases. Okay, so somewhere over here, I have a Dion state with some mass that we need to be heavy, or we would have already seen this state in the world around us. But then we need this monodromy picture. The whole spectrum has to be invariant, and theta goes to theta plus 2 pi, so we need to have all these other kind of shifted states. Okay, so we have this family of states. Okay, but now I'm telling you something kind of weird, because I'm telling you the mass of the electron should change in the background of an axion, and it should change a lot. because it's got to grow heavy enough that we haven't seen it. Now,
I'm sorry, I feel like I lost a thread of the transition.
Uh-huh.
The F prime, you're just saying, supposing it's a bigger theory and there's other fields?
no,
or-
sorry. F prime is some linear combination of my F and my magnetic F, just for the usual U1. It's like a different electric-magnetic duality frame.
Okay, so it has to be there in the theory.
It's
I mean,
there in
we
the
can't-
theory,
we
and
can't
it's
just
still
say, "Oh,
creating
we
the
don't wanna
same.
hear
It's
about
still
that."
creating the same photon field, so it still affects the Axion coupling to photons. But we're just defining this coupling in a different duality frame. We're saying this is the frame where this thing doesn't change when we shift theta to theta plus 2 pi. And what I'm saying is if that thing doesn't change when you shift theta to theta plus 2 pi, then our original gauge field has to change. And that means that every electrically charged object in the theory has to get magnetic charge in the background of the monopole. It's just like the inverse of the usual Witten effect. And that's what I'm saying is really bad, because now you imagine we have an axion field. The electron is supposed to be sensitive to the axion. Naively, turning on an axion should not give the electron a mass, because the electron mass breaks electroweak symmetry. So how can I give a VEV to a neutral scalar and produce an electron mass? And you could say, well, maybe it couples to the Higgs, right? Maybe we have this whole combination, something like this, right? So the whole thing, maybe there's a coupling to the axion that is also sensitive to electroweak symmetry breaking and is generating this mass. But okay, this is kind of crazy. For one thing, this is never going to give you a mass that's much bigger than the Higgs VEV, or I don't know how to interpret this anymore. It's some bizarre, strongly coupled thing. The other thing is I have the exact analog of the thing I talked about over here. If monopoles have this electric Dion degree of freedom, they generate a potential for axions when you integrate them out. If electrons have this magnetic Dion degree of freedom, they generate a potential for axions when you integrate them out. And so does every charged thing that exists in the standard model. And so now loops of just ordinary charged particles will generate axion masses. Okay, and now I shouldn't do this as a semi-classical calculation anymore. I should just do this, this is an actual light field I can try to integrate out. And I have some kind of coupling here and some kind of coupling there. And I would naively just estimate, I get an axion mass squared. It's like electron mass times this monopole mass times cutoff over axion decay constant squared times a log or something. I'm going to get a really big axion mass. So, so my conclusion from this is that no version of this story makes sense in the real world. Abstractly, as a statement about how you can couple axions to free photons, or even to maybe some interesting theories that don't look like the standard model, you could try to write these couplings in other duality frames. But if you want to talk about an axion that actually exists in the world around us, I claim there is no version of this story that makes sense, because all the charged particles we know are now coupling in these totally crazy ways, and it's just not a consistent theory anymore. Okay, so that was the punchline I wanted to get to. Basically, there are a lot of things that we know about the structure of axion couplings that come from just using the fact that our axion field is compact and our gauge field is compact, and using what we know about the structure of compact gauge theories. And these are things that are not necessarily obvious when you just write an effective Lagrangian, but they're part of the structure of the theory. And they imply these interesting anomaly inflow sorts of phenomena where, like, the monopole world line must emit an electrically charged particle for the standard axion coupling, and similarly an electrically charged particle must emit a magnetic degree of freedom on its world line if you have this non-standard coupling. Okay, so I think that's the kind of complete version. I think everybody has always, most people have always believed the statement that these couplings are quantized, but recently there has been this controversy about it. And I think that there was kind of a nugget of an interesting idea behind that controversy, which is this SL2Z frame. But I think that if you try to work out what this means, there's just no version of the story that can be consistent. Thanks.
assume to get the quantization of these two numbers of angle, you have assumed that your functional integral sums over all topological classes of your bundle,
Yes.
right? Because you could have restricted the sum and saying, I don't know, that the Chern number is a multiple of 10, in which case.
That would just change the exact quantization.
Yeah,
I mean,
but
that would just put some other integer factor in front of
Yes,
this.
you make it smaller, so n
Yeah.
will be z divided by 10.
Yeah.
Right.
That's a thing that you can do, yes.
So that's another way to get as close as you want to the real number. So if you really
Well, no, I mean,
restrict
it's going to give you a smaller set of
a smaller n, yes. I mean,
no, I don't.
this n will belong to z divided by what?
Oh, sorry,
the
right,
minimum
right. You are
Chern number.
you are right.
If I only integrate over the trivial
Yeah,
class,
let's see.
right, I get no quantization.
Yes. I have thought this through before, and I'm not quite remembering how the story goes. I want to say that. Yeah, I'm not sure. I think I had a reason for not thinking that that was chronologically viable, but I can't quite reconstruct what it is. It might just be that then you're introducing another kind of global symmetry, and we don't believe global symmetries exist in quantum gravity, and I don't think you can do that construction without creating. If you sum over things that are like multiples of n, then you have the Zn free-form global symmetry in the theory. And I don't think there's a good way to explicitly break it. And if you gauge it, you just get back to where you started. I feel like I had a better argument than that, but that's the only thing that's coming to mind at the moment.
I lost a little bit in your final formula for the action for this thing. That just in terms of the field theta.
Yeah.
What kind of action do I get out of potential as a function of the original?
What kind of potential? Yeah, so the potential looks like erase something to write this down. Yeah, so the potential basically is it's given by the sum over things that have different harmonics, but the leading thing is basically just like a cosine potential, cosine of theta times e to the minus s, where this s is this big number. And then you get a prefactor in front, which I don't quite remember. I want to say it's something like this, but it's something that has the right units that's built out of these two-dimensional scales. I think in the Polyakov case, the number in front basically ends up being the bev to the fourth, the Higgs bev.
And it's cosine of theta, not cosine of some constant of some kind times theta.
You get all possible harmonics out of the sum of different windings, and so the leading one will be just a cosine.
But sigma, which is the size of the monopole, right?
L sigma, yeah, it's at least related to it. I'm forgetting if the monopole radius is somehow like a geometric mean of the two length scales here, or if it's exactly that, but it's something.
So naively it sounds dangerous, right? Because it's exponentially suppressed, but QCD contribution have lambda QCDs there, right? Which is essentially the same exponent. And
but we already know there are small instantons from QCD, right? QCD is giving us instantons at all scales that are contributing as like lambda to the fourth, e to the minus 8 pi squared over g squared of lambda. And the point is that these are competing with sort of, m pi squared, f pi squared, which is roughly e to the minus 8 pi squared over some beta function coefficient.
Yeah,
actually.
But those would be aligned, right?
But there is a difference.
Because whatever comes from QCD would have a minimum
because
take it to zero,
exactly, because the ones are aligned, right?
Right.
So
Oh, sure, yeah, of
so-
course.
yeah.
I'm just saying that you
Right.
Yeah,
the
and
small
this,
instantons are not necessarily. If there are heavy quarks that have phases in their mass matrix, the small instantons are not necessarily aligned, and we usually don't worry too much about that, because this exponential is just way smaller than that exponential. Because of that non-trivial number that appears there.
Yeah, but always the worry with that argument was it makes assumptions about the matter content of your theory in the UV, and you can easily make it. Right? Actually, there's some attractive grand unified theories that have very large matter content, and
Sure.
you get to a very large alpha gut, and
Yeah.
that is not very much of an exponential suppression.
In some theories, that's true. I
Yeah,
agree.
yeah.
But there's no
Sorry, are you
argument
saying
that that's
you can make the
a
thing
generic.
big or small,
Yes.
depending on the.
Yes.
Oh, that would be fascinating if you could
But there are
discover an
theories where it can
axion
be small
and
ones.
find it's too light, and that tells you, or, you know, it would exclude certain.
Well, I think the interesting stuff is you can't make it without unnatural fine tuning, as far as I'm aware. You can't make it lighter than the QCD contribution piece. That's very hard. You can.
Anson Hook has a weird model that's supposed to do that.
Sorry.
Like summing
Anson-
copies of it.
Anson-
Oh
Yeah,
yes,
yeah,
yes,
yeah.
yes. I forgot answers. Yes.
And things that get shuffled around and somehow, I don't know.
Also, I mean, there is an irreducible contribution to the axion potential that you presumably could compute by just saying, you know, these monopoles are just charged black holes. And in principle, I don't even have to discuss how I made those black holes, because, you know, your theory coupled to gravity already has those solutions, right? Like magnetically charged solutions. So can I not estimate what the contribution from, you know, magnetically charged virtual black holes is to this axion potential?
Well, I think that's hard to do because the radius of the smallest thing that you would trust as a semi-classical black hole is model dependent, right? It depends on how far the cutoff is below the Planck scale. So
Yeah, but naively I would think, I mean, obviously the black hole is very large, so there's gonna be, I expect that would be e to the minus action, the you know, the sort of, I don't know, Reisner Nostrom action of that black hole. But obviously, as this black hole becomes Planckian, that becomes order one. So naively, your
But they
calculation
cannot
suggests
become
that,
order one. You know, at most you can make them of a radius equal to the cutoff. To
yeah, but that
demonstrate.
radius maybe it will be a further the Planck length, right?
Well, no,
something like
because there
this.
is a species number, and you know, e to the minus n is can be very
Yeah.
small.
Yeah.
Even with
I think you know we'll certainly get black hole contributions that are order something like that. John has a paper saying this, right? I think we'll get things that depend on the ratio of Planck and cutoff, but if the cutoff is low, then I don't know why this couldn't be.
I mean, for say if lambda is the string scale already, this is a very small number.
I don't know where the string scale is.
Ah,
in our
set to the
universe,
scale
but-
as in the 80s, 10 to the 16 GeV.
Oh, you're putting it all the way up at the, yeah.
I mean, even that.
It could be much
is
lower than
equal
that still,
e
but
to the
even-
minus 8 pi squared times 100.
Yeah.
That's actually low, 10 times. And there is maybe. Those seem irreducible but tiny when you can trust your calculation.
I mean, anytime you're talking about exponentials in the Axion quality problem, it's not that bad because you just need e to the minus 200 and something.
Yeah.
So-
Okay, well, let's not get out of the figure now.